In 1958, Canada built the fastest, most advanced jet the world had ever seen. A year later, it was cancelled. Every prototype destroyed. Thousands of jobs gone. To this day, people still ask, why? Was it politics, US interference, or something else entirely? This isn't just history. It's a story of ambition, sabotage, and one of the biggest what-ifs in aviation.
تحلق في الجو طائرات حاملة للصواريخ. إن التحليق على ارتفاعات صغيرة جدا يعتبر هاما كذلك، لأن ذلك يتيح الفرصة لتفادي الرادار والصواريخ والمدافع المضادة للطائرات، أي الاقتراب بقدر الإمكان من العدو على الأرض. تحلق في الجو حاملات صواريخ استراتيجية. وفي مكان ما في المحيط الأطلنطي ستتقابل حاملة الصواريخ مع ناقلة بترول طائرة. هذه محطة وقود على ارتفاع 12,000 متر. هنا نرى دقة الحسابات والآن في إمكان حملة الصواريخ أن تطير إلى أي نقطة في الكرة الأرضية وأن تنفذ الأمر الحربي. أطلق الصاروخ من على بعد مئات الكيلومترات عن الهدف، ومع ذلك فهو يصيب الهدف دائما بدقة، وفي إمكانه أن يحمل شحنة نووية. ذات الشحنات الذرية من أي نقطة ومن أي محيط. الحكومة السوفيتية والشعب يعتنون بالجيش عناية الأب ولا يبخلون من أجله بشيء. وتحمي القوات المسلحة أرض وطنها بدرع مأمون، كما أن اتحادها العسكري مع البلدان الاشتراكية الأخرى متينة. تتجه الصواريخ من ميدان العيد إلى ساحة الإطلاق. وسائل الدفاع الجوي والصاروخي قادرة على أداء المهمات الحربية الموضوعة أمامها بكل نجاح. ما زال هناك إمبرياليون ومتهورون مجنونون ومخبولون من الذين تهدد خططهم المغامرة بجر البشرية إلى حرب عالمية جديدة. ويجب على المعتدين أن يعرفوا أنهم إذا أشعلوا حرب فسينالوا ضربة قاضية خاطفة من قبل القوات المسلحة السوفيتية.
The 1950s were tense. The Cold War wasn't just a standoff. It was a race for survival. The Soviets had long-range bombers that could carry nukes, and guess who was sitting right between them and the United States? Yep, Canada. Our skies became the front line. The Royal Canadian Air Force needed a game changer, a plane that could fly faster, higher, and farther than anything else. Enter Avro Canada. They promised to deliver the world's best interceptor, and boy, did they deliver. The Arrow wasn't just a plane, it was a revolution. The delta wing gave it unmatched speed and maneuverability. The Iroquois engine could push it to Mach 2.5, double the speed of sound. And the avionics? Cutting edge. This was Canada saying, hey world, look what we can do. The first prototype, RL-201, rolled out in 1958. It was sleek, it was fast, and during its first test flight, it didn't just meet expectations, it blew them away.
By December, installation of hardware and many of the tests on the aircraft systems are completed to the point where engine runs can be started. The engines are run with and without afterburners, and further systems checks are carried out. The taxi trials, started on Christmas Eve, give test pilot Jan Zurakowski an opportunity to become familiar with the handling of the aircraft on the ground. They also permit further checks of the damping system, the brakes, the hydraulics, and many operating tests of the parabrake. At this time, there are still many problems that have to be solved and quite a few taxi trials that have to be successfully completed before we can think too much about the attempt on the first flight. Finally, on the morning of Tuesday, March 25th, the Arrow is ready for flight. The two chase aircraft which have been assigned to keep tabs on the in-flight performance of the Arrow, a CF-100 piloted by Spud Potocki and a Sabre piloted by Flight Lieutenant Jack Woodman, take off to assume their positions over the airfield.
Detection. I am coming in to take photographs. Stand by it. Controls are behaving quite nicely. I can see no oscillatory motions of any description in them. I think all this immediate undercarriage is fact that all the vibration disappears. I think the carriage is making this. That's right. This is the side door which is making. The door which comes and closes the undercarriage in the wing is fitting against the fuselage. I'll be accelerating up to 250 now. Roger.
From Frank, we confirm this. Up to 250.
Thank you. Behaving quite nicely. They are occasionally giving you a bit of a black puff of smoke coming out of them, Jan, but otherwise I can see there is no problem. All locked down now. And quite strong vibration straight away. Yes, this is the same door hitting against the fuselage, yeah. But it seems to be pretty solid there, though. Aerospace, I think it's still got a bit less, 1.5 degree. Side slip to right. That is Roger, Jan. As far as I can see from the back, no condition has changed. There was no change. The radar has all the time a tendency to go to neutral and then about 2 degrees port. Switching out the dampers now.
Fuel readings, please, 201.
Wind is 40 to 50 degrees, 10 to 15 variable.
Thank you. look on to the Arrow 201 there, overhead 4,000 feet, and east section on 32, please.
201, Toronto Tower, runway 32, 32, the wind is northeast at 10, the altimeter is 020, and your number 1 for 32.
Telemetry is touchdown.
Wonderful parachute, Jan, fine. Beautiful job. I was thought I was turning to the left and then I put the indicator down now. Okay, Jan, give me time. I want to photograph this. The elevator is about 3 degrees or 4 degrees up as far as I can see from here. Ailerons are nice and flush. Controls here seem to be quite normal, Jan. No problem.
Wind is 40 to 50 degrees, 10 to 15 variable.
201, Toronto Tower, clear to land, wheels down, lock 32.
Telemetry is touchdown.
Wonderful parachute, Jan, fine.
One down at 27, cleared to company.
After watching its historic first flight, the huge crowd of Avro employees and Air Force personnel greeted the arrival of the Arrow at its flight base.
Plane and the birth pains of a production line. Exclusive to News Magazine, this is the first public showing anywhere of these previously secret films.
Canada had officially entered the aviation big leagues. The Arrow was unstoppable, or so it seemed. Here's where it all starts to go wrong. By 1959, the Arrow was costing over $1 billion, more than the government could stomach. And then there was NORAD. The Americans were pushing for missiles like the Bomark to replace interceptors.
To counter this threat, the U.S. Air Force developed the Bomark missile, which was essentially a pilotless, remote-controlled vehicle that carried an atomic warhead. Although the Bomark weighed over 15,000 pounds, it had a slant range of over 440 miles. Its mission was to fly into a squadron of Soviet bombers. Once its proximity fuse sensed the bombers, its nuclear bomb would detonate, obliterating anything within range.
The Arrow? It suddenly looked like a very expensive problem. On top of that, Prime Minister John Diefenbacher wasn't a fan. He wanted Canada to cut costs, not build flashy fighter jets. Politics and economics were closing in on the Arrow, and the clock was ticking. February 20, 1959, Black Friday. The government cancelled the Arrow. Every prototype, tool, and blueprint was ordered destroyed. Why? Officially, it was to protect military secrets, but unofficially, theories abound. Overnight, 25,000 people were out of work.
Something is
Many of Avro's brightest engineers left Canada for the US, where they helped build things like NASA's Apollo program. Canada's loss became America's gain. But here's the thing. The Arrow didn't just disappear. It became a legend. Some say a prototype escaped destruction and flew to safety. Others claim Arrow technology influenced planes like the Concorde and even the US stealth jets. What's certain is this. The Arrow was more than a plane. It was a symbol of Canadian ambition, a glimpse of what we could achieve, and we dared to dream big. So what really happened to the Avro Arrow? Was it politics, sabotage, or just bad timing? We may never know the full story, but one thing's for sure, it's a legacy that refuses to fade. Thanks for watching. This is A+. Don't forget to like, subscribe, and let us know in the comments, what do you really think happened to the Arrow?
Templates have been made by photographic methods for use in the manufacture of the free flight and wind tunnels in Buffalo, who manufacture and test. Dimensional accuracy on the templates has been held to plus or minus 1 thou in order to meet the rigid requirements in manufacturing and testing. After preliminary cutting, the templates are filed in an optical filing machine with which the 1 thou wide line can actually be split. This kind of accuracy has been held on both templates and models which have been made at Avro and Cornell. In many cases, dial gauge indicators have been used along with the templates to achieve the required accuracy in the finished components or completed models. The manufacture of the templates and the models is a demanding operation, and the accuracy of the data received from the wind tunnel tests depends entirely on the faithfulness of reproduction of the model from the design. While a great deal of wind tunnel work will be done by NRC in Ottawa, disassembled models were first shipped to Buffalo in June 1954. After unpacking and checking of all components and detail parts, the model is assembled on a sting. This serves as a support for the model and as a pipeline through which passes the umbilical cord used to transmit the information which must be relayed from the model to the control room. One prime example of the value of the wind tunnel has been a design change made in the top lines of the canopy
to cure a turbulent condition at the tail, which was indicated in the tunnel tests. When the turbulence was found to exist, tests were carried out in the NRC water tank at Ottawa using a scale model wooden canopy. Progressive changes were made in the shape of the canopy and the turbulence largely cured. To meet the requirements of the tests, control surfaces at a variety of angles have been manufactured and may be installed on the model to determine the varying effects under changed conditions or attitudes. The control room engineers may change the conditions affecting the model at any time. They can, by means of television, observe the model undergoing testing, and they can directly see the result of the tests on various gauges and meters. The interpretation of the figures is done by the aerodynamics people, and the information is passed to the design and stress offices. They incorporate the required set of conditions or changes into the design and stress specifications. So far, 5 wind tunnel programs have been conducted at Cornell. Many more will be required.
Most of the aerodynamics tests are carried out in a Canadian government wind tunnel at Ottawa. Flutter analysis of the Arrow presented several problems that could only be adequately solved by the building and testing of a scale stiffness model to afford a practical check against theoretical calculations. Air is forced into the tunnel and the control stick is pulled back to effect a takeoff. Action of the control stick moves small auxiliary flaps which trim the model during flight. The model tilts up, obtains lift, and flies off its bottom support into the center of the tunnel. Avro commenced the spinning test program in January 1957. These tests discover what conditions will cause the aircraft to go into a spin and what control actions must be made by the pilot to recover normal flight. The dynamic scale model is launched with an initial rotation into the vertical airstream. Scaled to 1/24th size, the model contains a magnetically operated remote control mechanism for movement of the rudder and ailerons, pilot orientation and design information for an anti-spin parachute are other questions to be answered in further spinning tests.
Will be accurately transmitted so that a record may be made. This transmitted record will be the only one available since the model cannot be recovered after flight. The launching program got underway at Point Peter Range near Picton in December 1954. At that time, 2 of the crude models were released. The model and its booster rocket were first assembled and installed on the ramp of the launching platform. This was completed in the assembly shed, and the unit then moved to the launching site. Complete instrumentation was done to ensure that each unknown could be recorded in some way as the model flew at tremendous speed through space. Special cameras were set up at many vantage points to provide a visual record of the flight and to assist in plotting acceleration, speed, and direction. A radar tracking system was set up as an additional means of recording the flight performance. High-speed cameras were set up to record the action taking place at the moment the model and booster would leave the platform. If anything was going to go wrong at this stage, we would want an accurate picture which would help to tell us why. The ramp of the platform was elevated to an angle of 47 degrees for takeoff, and the whole platform leveled at the launching site in the final stages of make-ready for the first launching of a crewed free-flight model of the CF-105.
Kinetheodolite cameras were installed in 5 locations to track the models and provide results which, with triangulation, show the velocity and acceleration. This information, along with the telemetry figures, gives us an accurate picture of the behavior of the model. The model and booster assembly, installed on the launching platform ramp, are completely checked out at the launching site and all final preparations completed just prior to the launching of each model. The model booster combination leaves the zero-length launching platform and accelerates to Mach 1.9, at which time separation takes place and the model continues to coast. The accuracy of the design data and the calculations relative to this phase of the design program were proven to be quite good with the first two launchings. In the summer of 1955, final preparations were completed prior to shipping the first drag model to the Point Peter range. It was swung in this way to provide weight and balance figures which would be related to the records we would obtain in order to show drag and other flight characteristics. Investigations had been conducted with the use of area rule to determine the drag of the aircraft, and we found with the flight of these models that our experimental results were in close agreement with theoretical calculations.
Throughout the program, the free flight models have been changed as necessary to incorporate the changes in the original design which have been dictated by the results of wind tunnel tests of the scale models. The progress in the design as a result of information so gained is exemplified by these views of free flight models prepared before and after design changes incorporated as a result of investigation of the effects of area rule. All flights of the models are recorded in minute detail by a telemetry unit in order that a maximum amount of information may be obtained from each launching. Of the 4 models seen here, 2 are models for measuring drag and 2 are used for checking directional stability. The latest available resources of many sciences are represented in the extensive and intricate recording and computing apparatus employed to note and to evaluate the information transmitted from the free flight models. Here, the instruments used for transmitting information from the models are being calibrated on a centrifuge under high acceleration conditions. In addition to the firings which have been carried out at the Cardi Range at Point Peter, 2 firings have been carried out at Langley Field, Virginia, the facility of the National Advisory Committee for Aeronautics. The evaluation of drag in free flight models requires a very extensive instrumentation of the range which was not available at Point Peter at that time. The Virginia facility was also equipped with Doppler radar installations which are capable of high precision tracking of models in flight. The model and booster assembly installed on the launching platform ramp are completely checked out at the launching site, final preparations being completed immediately prior to the launching. After the model and booster assembly is mounted on the launching platform, the ramp is then raised to the launching position, an angle of 45 degrees. The model booster combination leaves the zero-length launching platform and accelerates to Mach 1.8 approximately, at which speed separation of the model and booster takes place. The model then continues in free flight. Concluding the program, model number 11 was fired on January 10th, 1957. The free flight model program proved to be a successful and relatively inexpensive method of obtaining the required drag and lateral and longitudinal stability data. Analysis of this data verified original prediction and helped to ensure the success of the Avro CF-105.